Aloha everyone. So in this project I'm going to teach a robot arm to wave using imitation learning with action chunk transformers. So it's basically similar to this project but probably not as advanced. So this project's by Zhao Fu, Tony Zhao and Chelsea Finn at Stanford University, and they've published some pretty amazing results, and they've also published their code online. So I guess teaching the robot arm to wave is basically the Hello World of autonomous mechanical processing. Now, when I was at university, I had a colleague who said to me, once you've done the Hello World, you're halfway to learning a programming language. Now, I probably wouldn't go that far, but it does overcome a lot of hurdles to building a robot like this. So there's basically 3 steps to this. The first step is to set up an environment to record our actions for imitation learning. The second step is to basically do our training on our network, which just involves the software, and I'm going to use the software that Tony's put on the Github, the ACT software, Action Chunk Transformers. And the third step is the inference. So it's basically like trying to get the mechanical arm to act autonomously based on the software. So this is the setup here for the first step, and I'll go through that with you now. So basically this is the master, which is the controller. So this is a robot arm, but it doesn't have motors on it, it just has potentiometers on it. And I got this because it was a little bit cheaper. So this one here that Tony's using, and the Stanford team, these cost about $6,000 US. So this one here was about 90 American dollars, and this one here was about 200 American dollars. So I could use the arm as a master to control, I could use 2 identical robot arms, and then I could just turn the motors off and read off these are serial servos, so you can just read straight from them to see what angle they're at. But this was cheaper and I wasn't sure what arm I wanted to use. So this is the X arm, which has 6 degrees of freedom from High Wonder. And then the other arm that I was looking at was the Wave Share arm, and that has 5 degrees of freedom. And then there's another one which is AR4, and that has 6 degrees of freedom. That's about $2,500, so that's a bit out of my price range. So basically I wanted to bring it in for about 1/10 of the price that the Stanford guys have done, and they said it costs $32,000 US. So I'm trying to reduce the price of everything, I guess, except I have got a fairly good computer. That's the only thing I really didn't skimp on too much. So this arm here can lift about 200 grams. The Wave Share arm, which is in the same price range, but it's only 5 degrees of freedom. It doesn't, on that the wrist doesn't rotate, will come in about 200 or 300 American dollars. And then I guess that lifts about 300 grams, and then the AR4 arm will lift about 2 kilos, and then the one that Tony's using here will lift about 750 grams, I think. But it's actually got quite a nice reach, this one, and quite good dexterity, the one that Tony's using. So anyway, so we've got the controller, so this is the master, this is the puppet, and then we've got a camera. And we've got the monkey here. So when the monkey's in the middle of the camera, the arm's going to wave to the middle, and when the monkey's on the right, it's going to wave to the right, and when the monkey's on the left, it's going to wave to the left. So basically, I want to teach the arm to wave at the monkey. Now, you do need a camera or some kind of sensor. I mean, a camera is the most obvious kind of sensor. Without a sensor for your environment, if you're trying to do autonomous processing, you're just swinging in the dark, both literally and metaphorically. So the camera is quite important. So I'll show you the setup. It's here somewhere. So I programmed it in ROS, and I'll show you. Hopefully it'll work. All right. So this one here on the left is the actual camera. So, and this one here on the right is reading from the messages that are sent. So this is the publisher, and this one here on the right is the subscriber. and its subscriber runs a little bit more slowly because I wanted to bring it into line with this robot arm, because the robot arm is, if I send messages to it too fast, you get some jitters on the servo, so I had to slow it down a little bit. So basically what I do is when I press start, it starts recording, and when I press stop, it stops recording. So I'm going to make this a little bit bigger so you can see it a bit better. Okay. So when I move this arm, let me move it actually towards the camera so you can just see it in the camera. Alright, so when I move the arm, this arm here, the real robot arm that actually going to do things moves, alright? So let's put that back now, back to its upright position. Alright, so when I press start, let me move this section to the right a little bit. So when I press start here, it starts recording the episode, and when I press stop, it stops recording the episode. Now in Tony's code, he has his episodes, they're all the same length, so they record for a certain length of time. But I didn't want them to all be the same length, so I was just using stop and start, but there was a little bit of, I guess, tweaking in the code that I had to do because like it tries to stack them with TensorFlow, and if they're not the same length then it throws an error. So when we start recording, and now we wave to the, sorry that was the wrong one, we wave to the right, so, okay, like that, and then we open up, and we rotate, like so. We basically open our hand, rotate our wrist. You can't really see that very well. And then we bring it back. Alright. So that's it, and then we press stop to stop the recording. This is the code here for recording the episodes, and I'll put this on GitHub with some commentary so you can have a look at it. But I'll just say quickly that, so this here has a ROS node which publishes to the image, which publishes to the topic joint states. So this is a publisher. I haven't written it very, it's not very complicated, it's all in Python. And I've used ROS 2, but not very advanced. And then this subscribes to the joint states topic, which this publishes to. So this subscribes, so each joint here subscribes to the state of this joint here. And then this publishes to the images topic. And then we subscribe to the images topic in our file, like in our episode file. So when we record our episode file, we subscribe to the image topic, which the camera publishes to. So this code here, I'll just show you this very quickly. This code here records into an H5PY file. Here we are. And this is exactly the same format that Tony uses on that Tony Zhao uses for his action chunk transformers code. So where we do need to be familiar with the models is on the inputs and the outputs. So Tony uses a fairly advanced transformer network, which sits on top of a convolutional neural network, and ResNet 18. And so we don't actually have to know every little nook and cranny of this network, but what we have to know is the input and we have to know the output. And so as long as we have that, as long as we're really familiar with that, we can pretty much plug in any model we want. I guess within reason, that's written in the correct software. So I'll take you through Tony's code next. I've also written some code to replay these episodes. So this is really good because it does help the familiarity with the data. So I'll show you that now. So this is like our replay episodes code. basically it sends the data in the file back to the robot arm. So let's have a look. So let's choose our 0th index, say, and let's run this. Okay, hopefully this will work. Oh no, it's not working because we've still got this running, and this has access to the arm. So we need to let go of the arm, release the arm, and now we can run it. Alright, so you can see the robot. Now it's waving to the left because the monkey's on the left. See how the monkey's on the left and the robot's waving to the left? Alright. Alright, now let's replay an episode in the middle. I think, from memory, episode 11 is in the middle. Right, let's have a look. Alright, yeah, see the monkey's in the middle here, so the robot arm is going to wave to the middle. Alright, note this image here is not the same as this monkey here, because this monkey is actually there, but that image is the image from the file that we recorded. Alright, now let's see if we can get it to wave to the right. Okay, I think episode 22 is to the right. I recorded 36. So I recorded basically 12 of each. Okay, yeah, so the monkey's on the right there, and now the robot's going to wave to the right. Let me just hold it down so it doesn't fall over. Alright, so in the next scene, I'll take you through Tony's code a little bit, mostly focusing on the inputs and the outputs, and then I'll show you how we can get that code, I guess, to train a network, and then after that we'll do the inference, and then we should be ready for the next step, which will be either adding another robot arm, adding another camera, adding some wheels, or some other feature to the robot. Now I'm going to take you through the action chunk transformers code from Tony Zhao to train the network, basically. So we've recorded the data, and we put this recorded data through this code, which is a transformer network. So they published a paper, and you can see this is the network here, and the code is actually pretty true to this network. So this encoder here is only used during training, and then this whole thing is used during inference. And here's the images which go through a convolutional neural network, which is the backbone, and then the joint states go in here, and we have an action sequence which we use at training plus the joint states. So this is all in the code, so we'll have a look at that. So what we really need is the joint states and the action sequences for training, and then we need the output as well, which is just a regression, basically. So basically there's two kinds of output. One is a regression, one is a classification. In this case we're using a regression which gives us how far, or the next position, the position of the servo, of the joint, basically. Alright, so this is the code here. Now I've forked this to my own repo, just because I have to make some changes. Now where I really have to change it is because Tony's Aloha, when they do their robot, they're using 2 arms, and they've got 6 degrees of freedom for each arm, plus they have another value for each arm, which is a binary value, which is a 0 if the gripper is closed and a 1 if the gripper is open. So that's 14 values they've got. So 6 plus 1, so 7 values for each arm. But I'm only using 6, so I have to change that, and that's hard-coded throughout the code, actually. So you basically, I've just got to find wherever they put a 14 and change that to a 6. and there were a couple of other things that I had to change as well. So we'll have a look at that code now anyway. And okay, I'm just going to pause it so I can get the code up. Okay, so while it was paused, I got the code up here, but let's just have a look at the README file. So in the README file, it starts off with this imitate episodes.py. So that's basically where we'll start, and then we've got all these variables, which we the only one I really had to change was this chunk size, because I had to make that the same size as my episode length. Right, so this is the code. This is the imitate episodes file that we start off with. So the main file, these are all our arguments. So the eval is false. This is just our directory where we have where we store the model weights, so that when we want to do the inference, we don't have to retrain the model. We can just use those weights. This policy is act, so this is basically the network that we're using. On-screen render, this is false. Task name, this is wave hello. Batch size, I'm using a batch size of 4. You can use a batch size which is a bit greater, but I'm just using, because I've only got 36 episodes, 36 examples, and they're all so it's because I don't have many, I'm just using a smaller batch size. So this is 2000. Okay, so now we're not so this is wave hello, so it's not sims. We're not doing a simulated, so we don't have to worry about that. Aloha script import task config. So this is the configuration basically. So let's have a look. Let's go to definition of that and our task config. So I've added this to task config, which is my wave hello. So episode length, number of episodes, which is 36, and I've put in the data directory. So I've added this data directory here, which is where my episodes are. That's this data directory here. I don't know if you can see that because that's probably pretty small. And then this is wave hello. So that's where my episodes are basically recorded. Okay, imitate episodes. All right. Okay, so now our backbone is ResNet. So if we look at the paper, let's have a look. Our backbone are these green things here. These are our convolutional neural networks basically. So we put our image here through this convolutional, which is like, these are already being pre-trained, so these know what features to extract. So that's the backbone, which is this thing here. And then our policy class is act, which is what we're using. So then we just have our configuration. LR is our learning rate, num queries, chunk size. So that's basically, this has to be the same as our episode length basically. Otherwise the tensors kind of, it'll fail because you're going to get two different size tensors trying to interact with each other. So this is basically our configuration for policy class act. Is-eval is false, so we don't worry about that. Okay, so now this part here is the data loader, and this is quite important. It's quite important to understand this because this is our input data, and what we really have to know, we have to know our input data, because that's what plugs into the network. We don't have to know the intricacies of the network as long as we know this. So a data loader is like an iterator or a sampler that just samples each part of the data. So we have training data and valuation data, and these are our statistics, which is just to normalize our data. Because so why you need these is because you could be measuring your joint angles in degrees or radians, or in my case I'm just taking it straight from the robot. So this is just a number from 0 to 1000, which represents an angle from 0 to 270 degrees. So because I'm just taking in this number, then I use these stats to normalize this number. So it would basically be equivalent if I was using degrees or radians. So now let's have a look at this load data function. Okay, so here we are. All right. So this is in our utils. Let me see. Okay, so what it does is this just divides up which ones we want to use for training and which ones we want to use for valuation. But so our training data is actually given by here, and this is our data loader, which is part of the PyTorch library. So if you need to do like a refresher on PyTorch, there's a really good tutorial, which is this one here, and this is part of CS330. And the lecturer for CS330 is actually Chelsea Finn, who is Tony Zhao's supervisor. So this tutorial ties in really nicely with the code that Tony's written for action chunk transformers. So this is our episode. Let's have a look at that anyway. And this basically goes through basically defines this get item function, which reads a file, an episode file, and extracts all the items. So these files, these H5PY files, are basically like a database kind of file. So everything in that file is like a table, and it has like a label, like a heading. So we have this action here, which has a table, and then we have observations QPOS, which has a table, and this observation QVal, I commented that out because I'm not using that. That's the velocity. This code doesn't use it anywhere else either, so I don't know why that line's included there. And then so this is the position of the puppet, of the actual robot. Action is the position of the master, and then these are the images, and I'm using images cam name here. These are the images here. So cam name is top, so that's the one I'm using when I run my code. If we look at, actually, is it in here? Yeah, so camera names here is just top. They're using cam high, cam low, cam left wrist, and cam right wrist. Okay, so we're at load data. All right, so basically what this function does is it returns here image data. So image data is just one image, so it samples a random point in the episode basically. So here we are, start TS. We just get one random point in the episode because we have this set to false. So we just get one random point in the episode, and at this random point we get the image and the QPOS data, which is the position of the master, sorry, of the puppet, not the master, it's the position of the actual robot. The action data, which is, it's all the data from the time we sampled to the end, basically all the positions of the master. So this is all the control positions from the time where we and isPad just tells us how far it's padded, because the episodes are not always the same length. So this way we can keep the episodes a consistent length. So I've made sure all these episodes are 50, which is greater than the maximum. The maximum was like 45. And then 6 is basically the number of joint states. Okay, so it returns all these. So if we look at the paper, actually we can see what these represent. Let's go down to the algorithm. Okay, so this is here. This will sample here, all right, in the algorithm. So D is like all our episodes, our data, and then the episodic data, or the data loader, will sample. So OT is the position of our robot, of our puppet robot. AT to TK is all the actions. So this is a vector of actions from our sampling point to the end. And then Z is our image. So that's basically what we're returning. We're returning, this is one single image, or like, I guess, one single time point. It can be as many images as we've got cameras. This is the position at one data point, and this is the position, all the positions from this time point onwards. All right, So that's something that we have to be, I guess, quite familiar with, because that's right where we can probably get some errors when we run the code. All right, so we load our data, and then the next thing we do is we make, this is for our, where we're going to store our outputs. These are our data stats. So this is basically, we can load this next time we want to do the inference, or our best model. And then we make our policy. So we're using the act. So this here is basically going to return our network. So this here returns, let's go back here. This here returns this network here. This is basically the policy, this network here. All right. So that's what that returns. And it's pretty much to the letter. So it builds our optimizer here. I mean, there's a lot of different, I guess it calls a lot of different different functions to do this. So this is our model, which is basically this, and then our optimizer, which basically does our backpropagation and steps through the model. So now when we call it, so let's just go into here. So this is our loss, right? So our loss is an L1 loss, which we're using for regression. Basically, it's the absolute value between the output of the model and the output we want, and we want to minimize this. And this KL loss is just like a regularization, and this should be in the paper as well. The loss, yeah. So that's our regularization loss, and this is our regression loss. Here they're saying mean squared error loss, but it's actually an L1 loss that they're using in the code. So yeah, I've just been using what they've got in the code. So when they return this loss, what PyTorch does is it won't return a number, it'll return a computational graph, right? So this loss, it has all the weights and all the network parameters in there already. Like it's like returning the formula. So we can kind of backpropagate through the loss, calculate the gradients, and then update all the parameters based on that. So it's not like just a number. PyTorch actually returns an object, and then everything is like we can take the partial derivative with respect to the parameters in that object in that computational graph. All right, so we're using the L1 loss basically here, f.L1 loss, which is good for regression because you want to get as close to the expected output as possible to that actual number, which is actually it's not like a class. Like if we wanted to do a class like what's the next letter or what's the next word, we would do a cross entropy loss. So the cross entropy loss will give us a look at the probabilities, and we'll try to maximize the probability of the correct of the correct one with respect to the training data. But this one will try to minimize. We'll try to make the output as close. So A hat is the output basically of the network, which is basically our predicted output of the network. So let's have a look at the model anyway. So let's have a look at that. All right. Okay, going there. Okay, so build backbone. So that's the backbone build transformer. All right. So, okay, so this is the model here. Okay, so this here is 6, right? This here is 6, but I had to go through and change. See this 6, this was a 14. I had to change all of these 6s, all of these 14s to 6s. All right, so there's quite a number of them. Okay, yeah, this state dim here and this build function, this we had to change as well. So make sure you've got this, because this is like your variable that that decides how many outputs and inputs you've got. Okay, so let's go back to our forward function here, and then it returns a hat. So these are our, oh no, that's the wrong model. Okay, that's CNMNLP. this one here. This one here returns a hat. So this is our DETRVAE model, which is the model that we're using. And a hat is basically our prediction, all right? So it's the action head, which we can see is defined up here. The action head, yeah. So linear and state dim. So state dim was the one that we had to set from 14 to 6. So we basically, this is the output of our model, which is the output of a linear neural network, and it's got 6 nodes and the hidden dimension, whatever you want to put that to, inputs. Okay, so 6 node output, and then that's what we got. That's what we use to calculate our loss, is the a hat, which is, it's also in the paper. If we go down here, a hat. Okay, so we predict a hat there. All right, so now I'll show you my inputs. So they're in this README file, and these are basically my parameters. So I can copy this, and let's see if we can copy that to the terminal. Open a terminal and see if we can run it. Okay, can you see that? Okay, so this is so what we had to do is, it's this chunk size here. Alright, so see how we see this error 102 and 52? That's because the chunk size is 50 more than it needs to be. So let's try now. Okay, there we go. Couple of warnings, but they don't do much, and then it just basically, we can see it's printing the loss after every iteration, and it looks like the loss is going down quite nicely. Valuation loss 1.4, training loss 4.6. That's because I think we've got a larger training set. But let's okay, now it seems to be going down a fair bit. Alright, okay, so that'll run for 2,000 iterations, and then in the next scene, hopefully we can do the inference. I've trained the network and I've got the inference working, and to get the inference working I just had to change the code a little bit, and I'll show you how I did that. But first I'm going to give you a quick demo. So basically this robot arm here is supposed to wave at the monkey a little bit to the right, so we'll see that if that works. Alright, now let's move the monkey to the middle and see if it waves to the middle. Alright, now let's move the monkey to the edge and we'll see if that works. Okay, well that seemed to work. So when the monkey was on the right, it waved to the right, and when it was in the middle, it waved to the middle, and when it was on the left, it waved to the left. Now, one thing I did, when I was recording, so when I was doing the recording with this, with the imitation learning, which this was the one I was using for imitation learning, I would do like 10 in a row of the monkey in the same position and the lighting the same. But I found that the result can vary. If I've got the lighting wrong or the monkey slightly moved, it can vary a little bit. So what I need to do when I'm recording my episodes, well, I need to keep this in mind for next time, is I need to change the brightness of the light and maybe use a noisier light or change the angle of the lighting, as well as slightly shift the monkey every time I do it, or whatever object I'm using. So that's a lesson learned. But I guess now I'll show you what I changed in the code. So when I first did the code, when I did the recording of the episode, I used ROS 2. So when the Stanford team presented their code for recording the episode, they used ROS 1, and I wasn't using ROS 1, so I had to change it all. I think they used Noetic, and I'm using Iron But so I had to change it all, and I rewrote all of the recording stuff, all of the record episode stuff in ROS 2. And the reason I used ROS 2 was just to facilitate communication, so I could use this, and if I wanted to have this and this on like separate computers, or the camera on a remote computer, I didn't have to have the devices connected to each other. So that's the great thing about ROS 2. It can facilitate communication over devices and threads. But of course, when I'm doing the inference, I'm not using this anymore. I'm just using the robot arm and the camera. So I just kind of put these in the same file, and I didn't use ROS for that. And it was much quicker to implement. But if I want to plug more parts in later, it's probably going to be more difficult. So I might have to rewrite that in ROS 2. But I guess that was the main reason I used ROS 2 for the episode capture, was because of the communication. But the other advantage of using ROS 2 is you can use simulation engines like Gazebo and Move It and even RViz. But I wasn't using simulation for this. But if at a later stage I wanted to do a more advanced robot in simulation, then ROS 2 would be perfect for that, or ROS. So when they do it, they have used this, what's called the real environment, and this basically creates an environment for their robot. And I created a much simpler modified environment just to do the inference. And all this is it just has, some of the same functions in there that get called. So I can just kind of plug this into the main code without having to worry too much. So I kind of just tried to copy just the function names basically and the signature, but it's a little bit simpler. So all it does is it captures the image. Oh no, sorry, this is mine. All mine does. So yeah, so it's the same functions here, but all it does is it connects to the robot. So that's just using the XARM library, which is in here, and then it just threads the input from the camera, puts that on a thread, just because when you've got a camera inputting to the computer, it can buffer the images, and I just want to get the latest image. So it just puts the image on this queue, on this D queue, which is from collections, and then when I want to access the image, I can just pop it from the queue. So get images here, and this just pops it from the queue. So that's all it does, and I'll put this code up on GitHub and you can have a look at it. But I guess the next part of this is to connect, to attach the robot arm to some wheels. So I've got this 6 volt, this 4-wheel drive 6 volt robot, but I'm not actually sure if it's going to be powerful enough to take this robot arm, and if it's not powerful enough, I'll have to get 12 volt motors. But so that's the next step, just to make it mobile, and then I'm going to attach more arms, and I'll attach another camera to this as well. So hopefully I'll see you in the next episode. Thank you.